Good morning, friends, and welcome back. Sorry, I took a little long to I decided to finish my breakfast in the break. Um, any questions on what we covered before the break? Let me start sharing again. So, before going for the break, we basically reduced the 7 dimensional variables to 3 non-dimensional terms. And let me tell you that mostly our goal would be to get relations like Nusselt is a function of Reynolds and Prandtl, and maybe some other terms, non-dimensional terms, which we will see. But this is mostly our goal. Okay, so if we can relate Nusselt number to Reynolds and Prandtl number, we can find out that what is going to be the heat transfer coefficient, therefore, for a given geometry, for a given fluid, and for a given type of flow. Okay, so my friend, these are called correlations. And as we will see later, that in convection, it is primarily these correlations which are very, very important. And many of these correlations, for very simple cases, flow over a flat plate or flow through a tube, it may be possible to get analytical relations for these, but otherwise, mostly for other geometries, these are correlations that have been developed empirically based on lots of experimental data sets. Okay, and as heat transfer engineers, now are we going to remember all these correlations? Hell no, absolutely not possible. Some of these correlations are very complicated to look at, etc. But we will have a ready reference through books, through whatever charts, etc. But you know where it comes is where, I mean, the skill that we have to pick up is, given a practical problem, can I reduce it to one of these geometries and use an appropriate correlation? Okay. See, hardly are you going to come up in when you're actually a designer on the field. You're not going to come across situations where it's flow over a bank of tube or flow over a cylinder or flow over a flat plate. Okay. But can I idealize these? Okay. Can I approximate the situation that is in front of me to be a combination of these geometries for which correlations are available, and then use it? Okay. All right. So now let us move on to what we were discussing before, which is governing equation. Now, governing equations, there are three. Two of them you already know. Continuity equation, momentum equations, okay, like Navier-Stokes equations. These we have already studied. Covered in fluid mechanics, right? There's a third governing equation that we are going to derive, we are going to discuss rather, and that is called the energy equation. Okay. Now, what does this help us to determine? This gives us pressure and velocity. the energy equation will give me the temperature field T. Now, thankfully, temperature at a point is the single value. It doesn't have a temperature in x direction and y direction. So therefore, unlike momentum equations where there is one equation in every direction, energy equation is only one equation. Okay, it's complicated, but it's a single equation that will give you the temperature of the fluid inside the boundary layer. Okay, that's all we care about. Okay, so let us move here. And for energy equation, we would say, as I mentioned, that for energy equation, we are not going to derive it here. We would say is derivation based on first law of thermodynamics. It's basically energy conservation. And please refer notes. Refer two notes. Okay. Let me write the correct English. Okay. So this I'm not deriving. Finally, I'm going to write the final form of the equation. It's a little long, but it is important to know what this equation is and find out the final form. So let me write that here. Final form of energy equation for 2D flow looks like this. Rho Cp del T del tau plus U del T del x plus V del T del y is equal to del x d del T del x plus del y d del T del y plus q triple prime plus mu times pi. Okay. So this is what it is. I may write here that in this form, the k is variable, but other properties like constant mu, rho, Cp. Okay. So look into this equation. Rho Cp we know, del T del tau, tau is time. Okay. This is time. Okay, not shear stress. Wall shear stress will write as T tau W actually. So this is time. Okay. UV we know the velocity components of the fluid in the x and y directions. Del x k is the thermal conductivity of the fluid. So this k now is called kf because in forced convection, this energy equation that we are going to solve is for the fluid temperature. Just like in momentum equation, we solve for the velocities, the fluid velocities inside the boundary layer. Here also we are going to solve for the temperature of the fluid inside the boundary layer. Okay. Q triple prime is any internal energy generation term Okay, mu is the viscosity, and phi is known as the viscous dissipation term. Actually, this whole mu phi is known as the viscous dissipation term, and the phi is given as this. Okay, del u del y plus opposite del v del x. Not always very easy to remember these. This whole squared minus plus 2 now it's this thing here, del u del x squared plus del v del y squared. Okay, this is known as the viscous dissipation term. Viscous dissipation function, actually mu phi is the term. So the viscous dissipation function. Okay, for a fluid with constant density. I mean, if density was not constant, then rho would have showed up here. Okay, so this is what it is. Now, for most cases, viscous dissipation term is neglected. Okay, there's also some pressure term that comes in the energy equation, which is many a time, because it's mostly negligible, we neglect it. So this is the final form. Okay, when I share the overall derivation, you will come to know of all the terms that play a role. Okay, but this is what it is. What I have put inside the box is important. So now, just by looking at this equation, let's make a few notes. Note, not note one. The first thing is, if the fluid is at rest, what happens? The fluid is at rest means u equal to 0, v equal to 0, and even this viscous dissipation term is also, function is also 0. There's no flow, then if u is 0 and v is 0, everything is 0. Okay, so now let us look into this. What does it mean therefore? uv is 0, phi is also 0. Does it look familiar? What is it?
Heat diffusion equation.
Exactly, the heat diffusion equation, right? So the equation reduces to the heat diffusion equation, because that was also derived based on energy conservation. Now you have additional terms, like with more number of because of the inertial terms. Okay. Secondly, I would say in most convection problems that we are going to face, q triple prime will be 0, and this viscous dissipation, which is given by mu times phi, is negligible. Okay. So many a times what we do is the last two terms go away, and what we are left with is the LHS and the first two terms of the RHS. Okay. Okay, so now let us take up the term, and let us take up the first example, which just builds on what we already know, which is known as the plane wall. or flat plate. We have studied this. Viscous flow from fluid mechanics point of view, we have studied this. We have come up with, I don't know why did this take a become inclined on my tablet screen. It's okay. All right. Now, what is the additional complication here? The additional complication is that I am now introducing temperature to what we have studied before, which is simple flow, right? So earlier we had flow at u infinity, but now I am also introducing something called T infinity. Okay, the fluid is coming at a velocity u infinity and at a temperature T infinity. Okay, I'm going to say that the wall, to assume it, let us say the wall is at a constant temperature Tw. Okay, now this is my x direction, this is my y direction, all that we already know. So what do we know from fluid mechanics? From fluid mechanics, we know that there exists something called a momentum boundary layer or a velocity boundary layer. I'm going to write it as delta. And over there, what happens? The velocity changes from 0 at the surface to whatever 99.9% of the free stream velocity. Right? And we have derived expressions solving the using scaling analysis and then use solving Blasius equation. We now know that what is going to be the thickness of this boundary layer, what is the velocity inside this boundary layer, what is the shear stress at the wall because of the viscous forces and so on. Okay, so this is what we know. Now, what happens to temperature? Temperature at the wall is Tw, higher than that of the fluid. Okay, so similar to velocity boundary layer, we also have a concept called thermal boundary layer. Now, what is that? What happens to the temperature? Before that, let us find out what will happen to the temperature. Okay, the temperature at the wall is Tw. Now, as you move away from the wall, the temperature will fall. And if you move very far away, you won't even feel, right? If this is a heated surface, if I touch it, of course, it's hot. If I go very close but not touch it, I can feel the warmth. It is still hot. If I go a little farther away, I don't feel it at all, right? So therefore, the temperature of the fluid also changes. If you measure the temperature of the fluid, it changes from the wall temperature at the surface to that of its to u infinity beyond a certain distance. Like this. And after that, it's u. Okay. Over here, the velocity is u infinity, and over here, the temperature is T infinity. So this distance over which the change happens from the wall temperature to that of the free stream fluid temperature, this is known as the thermal boundary layer. Okay, so this is the thermal boundary layer, whereas this was the momentum or velocity boundary layer. The effect of the shear or the viscous forces at the wall is felt within the momentum boundary layer. The effect of the thermal disturbance due to the heated wall is felt, quote unquote, felt within the thermal boundary layer. Beyond the momentum boundary layer, the flow happens as if oblivious to the presence of this plate. It's like an inviscid flow. It was happening, it is happening. Oh, did something come? Oh, was a plate introduced? Oh, I didn't know that. Maybe it is too far away. Similarly, if you're beyond the thermal boundary layer, you do not feel the presence of this heated plate. Okay, so friends, very important. The momentum boundary layer and thermal boundary layer, two distinct boundary layers. They are not necessarily the same. In fact, they are not the same. Okay. Okay, so let us see for this configuration, can I find an expression for heat transfer coefficient or an expression for Nusselt number? Okay, let us try and let us start. Before that, consider a flat plate. Maintained at TW. So it's an isothermal boundary condition, correct? Okay. The fluid at U infinity and T infinity flows over the plate. Resulting in heat dissipation from wall to fluid, because TW is greater than T infinity. Okay. So similar to momentum boundary layer, momentum or velocity boundary layer, there exists thermal boundary layer. Okay. Where the fluid temperature reduces or varies from TW at y equal to 0 to the free stream temperature I shall write it as delta T infinity. So over this boundary layer, what happens? Del T del Y. The scale says delta T over okay. All right. Now similar to what we did for flow over a flat plate, here also We have the same assumptions of boundary layer theory. Okay. Delta T, what are those assumptions? Delta T is much, much lesser than L, or at any point delta Tx sorry folks, I don't know what is happening with to OneNote. No, something is wrong. Shall I go to some PowerPoint? Let me do that. New blank presentation. Okay, let me try this here. Friends, you can continue. I probably won't be able to use colors, but that's okay. Okay, so what we are saying is the delta T would be much, much less than L. That's boundary layer assumption. Or delta T at a given X will be much, much less than, what am I writing here? Much, much lesser than X. The other thing was the gradient in the X direction, del T del X, would be much, much lesser than del T del Y within the boundary layer. Okay. Ready? Come on. Okay. Within the thermal boundary layer, this is what we have. Okay. Now, based on the same reasoning, and order of magnitude analysis. What happens is the energy equation at steady state it reduces to this at steady state. So the transient terms goes away, and what you have is u del t del x plus v del t del y is equal to k over rho Cp, which is alpha, okay. Of course, q triple prime tends is equal to 0. Give me a minute, friends. Yeah, I think it has come up again. To the pen. So q triple prime equal to 0 and phi is also negligible. So if you look at this equation, you see that there's a stark, I mean, there's a marked similarity with what we had uh, solved for momentum. There, what we had solved u del u del x plus v del u del y is equal to nu del square u del y squared. Okay. Now the boundary conditions were different. There the boundary condition was u equal to u infinity and u equal to 0, whereas at y equal to 0. But here the boundary condition is t is equal to tw y equal to 0, right? And t is equal to t infinity at y equals to delta t. Okay. So anyway, what is this? This is the boundary layer simplified form of the energy equation in the, please remember, this is valid only in this, within the thermal boundary layer, the x delta t layer. Okay. The other thing to note is q double prime at x is going to be minus k del T del y equal to 0 plus. And this is going to scale as, not equal to, but scale as K delta T over del tau. But delta T is TW minus TF, T infinity. Okay. So think about this. This is, let's take a step back and recap what we have done. What have we done? We have come up with a simplified form of the energy equation for flow over an isothermal flat plate. Okay. The temperature is constant on the flat plate. Okay. We will solve this. We will solve this. But a few things to note. The first thing is, just looking at the equation, you can see that the temperature distribution has a dependence on the velocity distribution, because you see the occurrence of U and V on the left-hand side terms. So therefore, the temperature field depends on the flow field. Okay, we knew this. You yourself say that if the velocity is higher, your heat transfer is going to be higher. Of course, we know this. From our practical experience, we know this. But now when we are trying to actually solve it mathematically, you can see that dependence being captured in this equation. Okay, that's one. Second, just look at the last expression. Higher is the slope of the temperature at y equal to 0 in the fluid side, 0 plus. Higher is the rate of heat transfer. Okay, if you look from more practical point of view, if you look at the scaling term that I've written at the end, what does it mean? It means that smaller is my thermal boundary layer thickness, higher is the heat transfer. If my thermal boundary layer thickness is thinner, or its thickness is lower, or if my thermal boundary layer is thinner, higher will be my heat transfer. In other words, it's a thermal boundary layer that is kind of a obstruction. It's a resistance, right? It would have been wonderful if the plate is at TW and just the next layer of molecules is at T infinity. Best. But that doesn't happen. Right? That doesn't happen. So therefore, there is a temperature gradient, and higher this temperature gradient, which means lower is the thermal boundary layer thickness, higher is my heat transfer. Okay. So therefore, remember the way we drew it. We had drawn the thermal boundary layer to be growing like this, isn't it? So definitely, you can say that the heat transfer is going to be higher at lower values of x and lower at higher values of x. Right? That way, it's a little different. The dependence is kind of inverse to that of shear stress. Shear stress, higher is the velocity gradient, and therefore lower is the thermal momentum boundary layer thickness, higher is the shear stress. But here it's opposite. Okay, so that's why I said in the last class, I said that when we are talking about cooling applications, etc., there's it's always a give and take. It's optimization. Okay, I want lower thermal boundary layer. I want lower boundary layer thickness, and so my shear stress is going to be higher, but my heat transfer is also going to be higher. You may ask me, well, you just said that the two boundary layers are different. Yes, true, but as we will see later as well, the growth is similar. Okay, there is a pattern. The momentum boundary layer also grows in the x direction. The thermal boundary layer also grows. Okay. Now, which one is thicker, which one is thinner? That is decided by Prandtl number, nu over alpha. Okay. What's the time? 53. Maybe we can go slightly ahead. Okay. Sorry about the one note problem, but we have to just live with. Can I change the color from red to something else? Sure, should be able to. Pink color, yeah. Okay, change it to dark blue. All right, so let me move on and write something like this. Let T star equal to T minus TW divided by T infinity minus TW. Okay. And again, this is what people have done. So we are assuming a similarity solution. Assuming as in somebody else assumed and showed it to be correct. That's why I'm assuming. Okay, I am not that smart. Assume a similarity solution. Okay. Recall what was eta? Eta was y by x times Reynolds to the power half for y u infinity by nu x. And what was f eta from my Blasius equation? That was psi times u infinity nu x. Right. So if you put these I'm sorry, friends. Looks like I lost my Microsoft Teams connection. Can you please let me know when we lost the connection?
Sir, you had written the expression for f of eta.
Okay. All right. So keep that in mind. It's already 9:57, so no point starting now. Okay. So we will continue from here from tomorrow, and we will complete this and move on to the other problems. Okay. So once again, I'm sorry. First one note and then this Microsoft Teams. Both of them started misbehaving towards the end of the lecture. Uh, Hopefully tomorrow will be fine. And okay, all right. Have a good day, and we will meet again tomorrow. Tomorrow we will also decide. Please remind me. We will also decide as a class when we want to have our next class test, the which would be on radiation and heat exchangers. Okay, it has to be in the following week, in the week of 25th. So we will fix up the date tomorrow. Okay. Thank you very much, and see you again tomorrow. Bye. Yeah, I'll be here for a 7 more minutes to answer any questions that you may have.